In this video, we will be putting a calculus spin on something we've learned previously, exponential growth and decay. We're going to show that exponential growth and decay, those formulas involving e, that they start as a differential equation. So our first example, we're actually going to use separation of variables and talk about separation of variables. Then in examples 2 through 6, we will talk about and model different exponential growth and decay problems. And then finally, the last thing that we will do, I'll do a couple bookwork problems at the end, and those, of course, will correspond to the ones that you have to do. So let's get started. Example 1, we're going to talk about separation of variables. We want to solve this diffie-q. Remember, a diffie-q is simply an equation that involves one or more derivatives. This equation just involves y prime. Now, if you feel more comfortable calling y prime dy dx, then go ahead and do so. If this variable was like a t instead of an x, it'd be dy dt. So it's dy dx because x is the variable we're dealing with. So I actually prefer that notation with separation of variables because we can clearly see dy and dx as two separate pieces as opposed to just y prime. So we'll have dy dx equals 2x over y. So I simply rewrote the problem using what's called Leibniz notation, and I hope I'm saying it right. I just looked it up on YouTube. He's one of the big hard hitters in calculus, so he was just a mathematician that died in, I think, the 1700s. So he, instead of using y prime, he came up with the two separate parts. Again, and this little d kind of stands for change in, again, because this is talking about slope. So it's like a very small little change in y divided by a very small little change in x. All right, so from here, we want to actually separate the variables and get everything with y on the left and everything with x on the right. Now I'm going to do this in just one step. I'm going to multiply both sides by dx, and then I'm going to multiply both sides by y. So when I do that, I'll end up having y dy equals 2x dx. Now we still have our differential equation, but we have separated the variables. So now we can integrate both sides. Please note that on the left, we're integrating with respect to y, and on the right, we're integrating with respect to x. We're actually going to be using the power rule for integration on both sides, so these are pretty simple to integrate. I'm not going to put a plus c, well, here, I will put a plus c, but I'm going to call it a plus c1. And then over here, I'm going to have the 1/2 times the 2, so those will just end up being x squared plus c2. Now, c1 and c2, or just plus c, that's just any constant. And so what we can do instead is just combine them on one side and just have one singular plus c. So really, when we integrate this, 1/2 y squared equals x squared plus c. It doesn't really matter what side it's on. If we want to make this look a little bit nicer, mathematically, what we can do is have the x and the y on the same side and just equal to the constant. That would be standard form. And also standard form, the coefficients of all of our terms should be not fractions. So I'm going to multiply everything through by 2, which is totally legal. So I'll have y squared, then multiplying that x squared by 2 and also subtracting it to get on the same side. And then instead of writing 2c, it's just the same thing as c, again, because c is just any constant. So 2c means the same thing as c. And so we have successfully solved this differential equation. In many applications, the rate of change of y is actually proportional to the value of y. So writing that out mathematically, it's a differential equation because it involves a rate of change. We have dy dt with respect to time, so the change in y with respect to time is proportional to y. This k is just some constant. It's actually the proportionality constant. We're going to show that when we solve this differential equation, we'll actually get the y equals c e to the kt. This is our exponential growth and decay model, and this is something that we've learned previously before calculus. So let's actually do that proof and show that when we solve this differential equation, that we get the y equals c e to the kt. This represents both growth and decay, where when k is greater than 0, we have growth, and when k is less than 0, we have decay. Some common things that you probably have done before with exponential growth and decay are like continuous or continuously compounded interest rates, or that would be exponential growth. And then exponential decay, probably the biggest example that you see with that is Halflife in like chemistry or biology. All right, so let's prove it. Let's prove that when we solve that differential equation up there, dy dt equals ky, that we will in fact get this lovely guy right here. So first we want to separate our variables. So I'm going to actually divide both sides of this by y and also multiply both sides by dt. So we'll have 1 over y dy on the left by dividing both sides by y, and then multiplying both sides by dt, I'll have k dt. From here, I want to integrate both sides. So when I integrate 1 over y dy, I'm going to get the natural log of the absolute value of y. And then remember, I'm not going to put the plus c on that side, I'm just going to put it on the other side. Over here, using the integration, actually I'm not going to use the power rule because I'm integrating with respect to t, so k is just some constant term. So the integral of k with respect to t is just kt, and then of course we have our plus c. Now from here, we're going to use the fact that this is an exponential form, and we want to get it into logarithmic form. Since it's natural log, we know that the base is e. So we'll have e raised to this exponent right here equals y. So e to the kt plus c equals y. Since e to the whatever always produces a positive output, I don't need these absolute value symbols here. The next thing that we're going to do is a little bit of tricky mathematical maneuvering. Again, we want y to equal c e to the kt. Let's see how we can get there from here. Now, because we have two things being added in our exponent rules tell us that we can write it like e to the kt times e to the c, because when we're multiplying powers with the same base, we add our exponents together. So I'm kind of going the other way that way. And I'm actually just going to call this c sub 1, just you'll see in a second. Now, e to the c sub 1, that's just a constant on its own. You know, e is just 2.718 ... c sub 1 is just some constant, so we can actually rewrite this as c, just in general. So we'll have y equals c e to the kt. I guess I don't need to box it. I wasn't solving. I was just proving that when we solve this differential equation, growth and decay, we get our growth and decay model. So just as a quick reminder, an example of exponential growth is when our k value is greater than 0. So I'm just giving examples as if c was 1 and if k was 1 or negative 1. As you can see, we've already looked at the graph of y equals e to the x or e to the t, and this is simply the decay model, 1 over that, when k is negative. So just as a quick reminder, exponential growth and decay, they're both exponential functions. They can model a lot of real life phenomena, and we use them a lot in applied problems. All right, let's take a look at our first example with the actual model. So we're shown here that the rate of change of y is proportional to y. So we know that dy dt equals ky. And we just did that proof before, so we can come to the conclusion that y equals c e to the kt. So again, we did this whole proof. I'm just taking this English sentence and turning it into a mathematical one. It happens to be a diffie-q. We already did the proof. That leads us here. Then we're given some initial conditions. We're told that when t is 0, y is 2, and when t is 2, y is 4. We need two conditions because we need to solve for both c and k. So because we have two things or two variables we need to solve for, we need two pieces of information. Once we find c and k, we're going to be able to solve what y is when t is 3. So I will first plug in this information. So I'm going to plug in 0 for t and 2 for y. So I'll have k times 0. So that just ends up being e to the 0. We know that e to the 0 is just 1, so we find that c is 2. That makes sense because c is like our initial value since it's at time equals 0. So anytime time is 0, we have e to the 0, which is just 1. So c is that initial idea. That only doesn't work we'll see later with something called Newton's law of cooling, where we have a plus or minus something over here. All right, so we know that c is 2, so let's simply rewrite over here with what we know. We know that y equals 2 e to the kt. Next, I'm going to use my next condition and plug in to solve for k. So I'll have 4 equals 2 e to the k times 2. I'm going to divide both sides by this 2 out here, so I'll have 2 equals e to the 2k. From here, we're going to take the natural log of both sides. So we'll have the natural log of 2 equals the natural log of e to the 2k. We do this so we can use the power property of logarithms and bring that 2k out in front, times the natural log of e, which is just 1. Then we'll divide both sides by 2, and we'll find that k equals the natural log of 2 over 2. Using our calculator, we'll find that as a decimal to be 0.3466, I rounded there. So our overall equation, or our overall model rather, is y equals 2e to the 0.3466t. Because k is greater than 1, it's a growth model, or greater than 0. Because k is greater than 0, it's a growth model. Now we want to solve what is the value of y when t is 3. That's a pretty simple plug and chug, and you're just going to use your calculator. And we'll get that as a decimal to be approximately 5.657. As I mentioned before, a very common application of exponential decay is Halflife, and probably the most common thing that I know as like a non-super sciencey person, the most common thing I've heard of Halflife being used for is carbon dating. But we can use it in a lot of different ways, to figure out how old something was. Basically, Half-Life is exactly what it says, it's how long it takes for half of something to remain. So that is clearly exponential decay, because half of half of half of half, it's never going to quite hit 0, it's never going to go away, but we keep halving every single time. So we're going to see that anytime we deal with Half-Life problems, we're going to end up with 1/2 in our problem at some point. Here, just from your book, I snipped some of the common half-lives. We can see that different elements have vastly different half-lives, like 24,000 years versus 25 seconds for half of a certain amount to remain. So this example here is dealing with plutonium, and this 10 grams of it was released in the Chernobyl nuclear accident. We want to know how long will it take for the 10 grams to decay down to 1 gram. So we know that we have exponential decay, so I'm just going to write out my problem, my model rather, y equals c e to the kt. That's what we're using. Well, we know that when time was 0, because we're starting, we're not told specifically time is 0, but we know that when time is 0, initially we had 10 grams of the plutonium isotope. So officially, this piece of information, I guess I'll go to there, is telling us that when t equals 0, y, the amount of that plutonium isotope, was 10. This is actually going to mean that c is 10, and here's why. If we plug in this initial condition, we can clearly see that we'll have 10 equals ce to the k times 0. E to the 0 is just 1, so 10 is c. Now, we don't need to go through all of that. If you realize that with these exponential growth and decay models, when you're using this model right here, the initial condition is c. So we'll have y equals 10 e to the kt. So now we need to find k. Let's think about this scenario. We know that because it's this specific isotope, Pu-239, it's going to take 24,100 years for that 10 grams to halve itself. So to go from 10 grams to 5 grams, it's going to take 24,100 years. Let's write that out as another initial condition. So I'm going to underline this because that's giving us information. So this is saying when this many years have passed, so when t equals 24,100, we know that the amount remaining is 5 grams. Again, it doesn't say 5 anywhere in the problem, but we got the 5 because of half-life and that we started with 10. So we're going to use this initial condition to plug in. Then I'm going to divide both sides by 10. When I divide both sides by 10, what's going to happen? I'm going to have 5 over 10. That's 1/2. So with these half-life problems, we do end up dealing with 1/2. Now from here, I'm just going to solve in the same way that I have been solving our exponential equations. We're going to take the natural log of both sides. Again, we do this so we can use that power property of logs to bring that exponent out in front. So the natural log of 1/2 or 0.5, however you want to write it, equals 24,100 k times the natural log of e, which is just 1. Then in your calculator, you're going to do the natural log of 0.5 divided by 24,100 to get your k value. In my calculator, I got negative 2.876 e negative 5. That, of course, means times 10 to the negative 5th. So this means I'm going to move my decimal point 5 units to the left. So 4 zeros. So this gives us our model. Again, I have not solved yet. I've just come up with my model based on the information. So here's my decay model. Again, because our k value is negative. So our decay model is y equals, remember our c value is 10, e to the negative point, this huge number, times t. So this is our model right here. We can use this model to answer the question. How long will it take? So what is t when that 10 grams goes down to 1 gram? So we're basically asked, what is t when y is down to 1? So I'm going to plug that in. So again, this means what is t when y gets down to 1? So clearly we should know that it's going to be more than that 24,100 years because we need to keep decaying past that 5 grams. So if 1 equals 10, e to this whole thing. Dividing both sides by 10, I'll have 0.1 equals e to this whole thing. Then taking the natural log of both sides, we can sort of see a pattern here. I don't need to write everything out. I'll have the natural log of 0.1 equals this large decimal here, actually small decimal. Dividing both sides, we'll get t is approximately 80,058. I guess 0.5 if that half year really matters there. Again, that's in years, which makes sense. So after 24,100 years, our 10 grams of this plutonium isotope went down to 5, but then after another 24,100 years, it went from 5 to 2.5. Then after another 24,100 years, 2.5 grams went down to 1.25, and so on. So that's why this follows that decay model. This problem is about population growth. We are going to actually learn how to do a problem when we're not told the initial condition. So we're not given when t equals 0, y equals this, and that doesn't just give us our c value right away. We're going to do a little bit of algebraic manipulation to find it. In this problem, we have a population of fruit flies increases according to the law of exponential growth. So boom, we know that k is going to be a positive number. We're told that there were 100 flies after the second day. So I'm going to write that out. So when t equals 2, so in this case, t is days, our output of flies was 100. And then after the 4th day, we know that y was 300. We want to know in the original population, so when t is 0, what is y? So again, these two are going to give us our model. And the last one, we're going to use the model to answer this question. All right, let's get to it. Again, this one's a little different. I can't just find C right off the bat. So I'm going to do some plugging in here. I'm going to actually have two equations. So instead of y equals, I'm going to have 100 equals CE to the 2k using that first initial condition. I just like to write the 2 in front. Then the other one will give me a very similar one. I'll have 300 equals c e to the 4k. What do these two problems have in common? C and also k. But what we're going to do is solve one of them for c and do some plugging in. Now, it doesn't really matter which one you use. I can't remember which one the book does, which c they solve for, but I'll just solve for c in this first equation here. So solving for c in that equation means I divide by e to the 2k on both sides. So let's write what I did here. I have 100, and you can write this as 100e to the negative 2k, or you can write this as 100 over e to the 2k. Either or is fine. I think your book writes it this way. So let's write what we did. We're going to substitute to solve. So solve for c. Then we're going to sub in the other equation. All right, so I'm going to sub this in for c. So I'll have 300 equals 100 over e to the 2k times e to the 4k. Solving this, I am going to see what I end up getting here. I have e to the 4k over e to the 2k. So I can subtract. So because I'm dividing powers with the same base, I can subtract the exponent. So I'll end up having 4k minus 2k as my exponent, which is just 2k. So 300 equals 100 e to the 2k. Then I'm going to divide both sides by 100. So I'll have 3 equals e to the 2k, taking the natural log of both sides and using the power property, dividing by 2, that will allow us to solve for k. K, using our calculator, is 0.5493. That makes sense that k is positive. Now I'm going to solve for c here. So I know that y equals c e to the 0.5493t. Now you can use either initial condition to solve for c. I'll just pick this first one because the numbers are smaller. So I'm going to plug in 100 for y equals c e to the all this times 2. Now I'm not going to take the natural log of both sides here, and that's only because I'm not looking to find something that's like up in the exponent. I don't need to find something that's stuck up in the tree. I don't have to log both sides. Instead, I'm going to see what this number is. I actually got 2.9999, so I'm just going to write it as 3. So we have 100 equals c times 3, and dividing both sides by 3 will give us 33 1/3. We're talking about fruit flies, so I'm just gonna like write it as 33. Now this is actually solved now, because remember we wanted to know how many flies were in the original population, but just in case I want to make sure that we know how to write the model. So our overall model, our decay model, would look like y equals 33. I guess you can put 0.3, but it doesn't really make sense since we're talking about a being. So we'll have e to the 0.5493t. Asking about the initial condition, you would plug in 0 for t and you would just get 33. So we know that there were 33 fruit flies at the beginning of the experiment. So I did get this snippet here from your textbook. This is showing the model graphically here. So we can see that this was our model right here, and we had this condition and this condition. Now we can actually do this on Desmos, doing an exponential regression. So let's actually explore how we can solve this on Desmos as well, and not having to do it fully algebraically. So here is the Desmos graph. Note that all I did was input a table, and I gave those two initial conditions that we were given. Now, I obviously can't call them t and y. I'm just calling them x1 and y1. That's what Desmos defaults to. So doing the regression, we've done a few regressions in Desmos, but we want to make sure you have not just y and x. They're literally called y sub 1 and x sub 1, so you're going to have to label them as such. And so we note that we are told that we follow an exponential growth model. So we know that when we do the regression, we're going to have y sub 1 is approximately ce to the kt. Now in this case, we just said that's x sub 1 instead. Now let's see what we are finding. It tells us that c is that 33.3. Perfect. And it also tells us our k value. So it actually gives us the function, which is really nice. Then, once we're given this function, we can just plug it right in. So I just plugged in the function. I put the 0.3 in there. It shouldn't matter too much. But here, if we want to take a look at some table values, we can clearly see that 33.3 is on there. Again, I put the 0.3 just to put it, but if we zoom out, we can see that this is our exponential growth model. And instead of just e to the x, where our y-intercept is 1, we have that 33 out in front as our c, which gives us our initial condition, or our y-intercept. So that's how you can use regression on Desmos. If you're just given 2 coordinate points, you can use the exponential regression, which looks just like this. Here is example 5, declining sales. So already I'm thinking exponential decay. We have 4 months after this company stops advertising. It notices that its sales have dropped from 100,000 units per month to 80,000 units per month. The sales are following an exponential pattern of decline. What will they be after another 2 months? Now, this is different from the exponential Halflife, like decay problem, because t there was measured in years. It doesn't matter what you measure t in, so long as it's consistent throughout the problem. So in this case, our t is going to represent months. We know that k is going to be less than 0 because it's exponential decay. Let's think about what conditions were given based on this information. It looks like when t was 0, y was 100,000. That was our initial condition. And then also we are told that 4 months after we got down to 80,000 units. So when t was 4 months, the output of the company was down to 80,000. So we can see that this is decay. It's inversely proportional. As t gets larger, y gets smaller. We're decaying. Then we're asked, what will the sales be after another 2 months? So t is not 2, it says another 2 months. When t is 6, when t is 6. All right, 4 months, another 2, there we go. What is y? So just so we're completely aware, these 2 pieces of information are going to give us our model. They're going to solve for c and k. Then this is the question that we want to use our model to answer. Now we know since this company's advertising output is, or like its sales, I guess, is decaying, then we know that clearly after another couple months, it's going to be less than 80,000. So if you get an answer that's greater than 80,000, then you're wrong. I actually just had to re-record this slide because my brain's like, oh, when t is 2, what's y? And I ended up getting 89,000. So I was like, that doesn't make sense. It can't go up again. I realized it said another 2 months, so now I'm re-recording the slide. Number sense for the win. All right, here we go. We're told that when t is 0, y, this is our initial condition, so that is just c. That's c, so it's y equals 100,000 e to the kt. If that confuses you, go back to the other couple problems we've done solving for that c here when t is 0. Then we want to use this condition to solve for k. So I'm going to plug in there. So I'll have 80,000 equals 100,000 e to the 4k. Dividing both sides by 100,000 will give 0.8 equals e to the 4k. Taking the natural log of both sides, we'll end up with the ln of e to the 4k. Using the power property, I'll have 4k ln e. And solving for k will give us approximately, and I'm just rounding, negative 0.0055 It says 785, so I'll do just to 8. All right, now I have found my model. Let's write the model out. Our model is y equals 100,000 e to the negative 0.0558t. I'm going to now plug in 6 for t. And I don't need to write all that out, but I have 71,548. I'm just going to keep it at a whole number here. So that's going to be units per month at t equals 6 months. Example 6 deals with Newton's law of cooling, which let's take a look at what that states. It says that the rate of change in the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. Writing that as a differential equation will give us that dy dt, so the rate of change in the temperature of an object, so where y is its temperature over time, so changing with respect to time, is proportional to the difference between an object's temperature, which y is the object's temperature at any time t, and then it's the proportional to the difference between the object's temperature and the temperature of the surrounding medium. Normally that's just room temperature. So basically, if you brew yourself a super hot cup of coffee and you put it in your room, which is probably like 70 or 71 degrees, it will eventually cool from whatever it is. I don't know how hot your coffee is, maybe 100 degrees? I actually don't know. And it will eventually level out to the temperature of the surrounding room, so 70 degrees. Now, it will take some time. It will cool off quickly, and then sort of the rate will slow down because it's exponential decay. So it will take kind of a long time to get there, but it will drop pretty fast at the start. Now, there are some ways when this doesn't work as well. That's why we put things in like thermal insulators and things like that to slow down that decay. All right, let's take a look at an example. We want to let y represent the temperature in Fahrenheit of an object in a room whose temperature is kept at a constant 60 degrees. So it's a pretty cold room. So our T submedium is 60 degrees. Then we're told that the object cools 10 degrees. So starting at 100 down to 90 over T equals 10 minutes. How much longer will it take for its temperature to get down another 10 degrees? So we're going to actually see that since it takes 10 minutes to decrease the first 10 degrees, it's most likely going to take longer to decrease the second 10 degrees. It's not a linear relationship. It's not just going to take another 10 minutes. So let's take a look at how we can set this up. We'll start with dy dt, so the rate of change of the temperature over time it's proportional to, so it's a k, and then we'll have y minus, and in this case we have 60 degrees for like our room temp. So now we have some initial conditions. We know that when T is 10, we have a output temperature of 90, and then we want to know when T is what, our temperature will then be 80. Now, if you look here, we actually have to solve this differential equation, which is pretty exciting. So here's where the calculus comes into play. I am going to separate my variables. So I'm going to multiply both sides by dt, and then I'm going to divide both sides by y minus 60. So I'm going to have 1 over y minus 60 dy equals k dt. What's next? I have to integrate both sides. So let me write what I did here. I separated the variables. Then I'm going to integrate both sides. So we'll integrate in orange here. So this is simply the natural log of the absolute value of y minus 60. That minus 60 doesn't do anything to our natural log. If we let u be y minus 60, we'd have 1 over u. And then du would just be 1 dy. So it's not, this minus 60 is not changing anything for this 1 over y. integration here. And of course our plus c we'll just put on the right hand side, so this will be with respect to t, remember. It's kt plus c. Again, it's not going to be 1/2 k squared, right? We're not integrating with respect to k. We're integrating with respect to t. So this is just some number. It'd be like the integral of 3 dx. It's 3x. So that's how we're getting this right here. So now we want to go from this logarithmic form to exponential form. So our base is e because it's a natural log, and we're going to have kt plus c up there equals y minus 60. Again, I can drop the absolute value, and that's because any output of e to the something is always positive. Now from here, I want to solve for y. So I'm actually going to call this c sub 1 again. I didn't have that forethought there. Now from here, using the properties of exponents, this is really e to the kt. This is similar to what we did earlier with the proof. Equals y minus 60. Solving for y, I'm going to add 60 to both sides. I'm also going to use that trick where this is just e to a constant, which is just another constant. So this is c e to the kt plus 60. And that is what our y equals. I'll write y equals on the left. So that's our model. So we can see that this is slightly different because we have a plus or a minus something over here. Normally it's going to be plus with Newton's law of cooling. It just kind of depends on how hot something is initially. So now we want to know how much longer will it take for the temperature to decrease to 80 degrees. But before I can do that, I have to note that I still have c and k to solve for. So I actually need 2 initial conditions, and this is something that I didn't write down in the beginning. Looking back, I wasn't going to re-record this whole slide, so instead I need to realize that I actually have one more initial condition. We actually know that when t is 0, like right when that thing is at its hottest, like its temperature was 100. Then after 10 minutes, the temperature was 90. After how long will it be 80? I just forgot this initial condition. But again, just kind of mathematical sense, right? We're not all going to get everything right from the very beginning, even if you've been doing it for 10 years. Okay, so let's plug in some stuff to solve for c and t. So I'm going to actually use this first initial condition to solve for one of them. Let's see which one it finds us. So if 100 equals c e to the k times 0 plus 60, this one's pretty simple. We're going to end up seeing that since e to the 0 is 1, we have 100 equals c times 1 plus 60, so c is 40. So that's pretty nice. So here's what we have so far. We have y equals 40 e to the kt plus 60. Now I'm going to use this piece of information to plug in to solve for k. So a lot of the same stuff over and over. Solve 10k plus 60. We want to first subtract 60 from both sides, then divide by 40 on both sides. So I'll have e to the 10k over here. So I have 0.75 equals e to the 10k. I'm going to take the natural log of both sides. So I'll just get 10k. Dividing by 10 will give us a k value of negative, which again, it should be negative. It's decay, 0.028. So I'll just do 88. That's fine. Okay, so our model, our full model, so this is sort of the model, this is like the specific, so this is like the general model, and this is the particular, is y equals 40 e to the negative 0.0288 t plus 60. So now we have to answer our question. What is t when y is 80? What is t when y is 80? Let's plug it in and see. So we'll have 80 equals 40 e to the negative 0.0288 t plus 60. Subtracting 60 and dividing by 40 will leave us with this. And so I'll have, I'll take the natural log of both sides, so I'll get the natural log of half equals the natural log of e to that. Using the power property, I'll bring the exponent out front. And dividing both sides by negative 0.0288, we will get our answer in time. And it's about 24.1. Honestly, I forget what the time is. Oh, it's in minutes. That's right. All right, so about 24 minutes. Now, that means, this is kind of a tricky question. It kind of took me by surprise too. This means overall it takes 24.1 minutes to go from the initial 100 to the 80. That's what that means. But it took 10 minutes. This question is asking us how much longer will it take? So we already accounted for 10 minutes. So this is going to take 14.1 minutes longer. So just be careful with that. That one got me too. Let's do some book practice problems real quick. I'll do number 1, 7, and 9, and then just 11. Okay, so number 1, 7, and 9, we want to just solve the differential equation. So we have dy dx equals x plus 2. We do want to separate our variables. In this case, we only have the dy for y. I'm going to multiply both sides by dx and get x plus 2 dx. Integrating both sides, I'll have the integral of 1 dy equals the integral of x plus 2 dx. The integral of 1 dy with respect to y is y. The integral of x is 1/2 x squared. And the integral of 2 with respect to x is plus 2x. And then we have plus c. If you took the derivative of this, you would end up getting x plus 2. Number 7 is a little bit more complex. So number 7, we have, I'm going to just rewrite it as dy dx, even though it's y prime, equals the square root of x times y. So separating the variables, I want to multiply both sides by dx and also divide both sides by y. So I'm going to end up having 1 over y dy equals the square root of x dx. When we integrate both sides, I'll have the integral of 1 over y dy equals the integral, I'll write x to the 1/2 dx. Now, integrating, the integral of 1 over y dy is the natural log of the absolute value of y. Over here, I'm going to use my power rule for integration. We've done this one so many times. I'm going to add 1 to 1/2 and get 3/2, so that's what I'm dividing by. So 2/3, x to the 3/2 plus c, making this look a little bit nicer. I want to get like y equals, so when I do that, I'm going to go to exponential form. So I'll have e to the whole thing over here, 2/3 x to the 3/2, so I'm going to write that as the square root of x cubed. And then we have that plus c up there, but we've seen a couple times today that that's just going to be a c out front, and that's going to equal y. There we go. And number 9, it's a little more complex, but it's still kind of the same amount of fun, if not more. So I have 1 plus x squared times dy dx minus 2xy equals 0. All right, this one's a little bit more of a doozy. Let's see where we want to start attacking it. All right, I don't want to distribute the dy dx through because I really want dy dx equals. So let's get dy dx equals. I'm going to do that in 2 steps, just in one. So I'm going to add 2xy to both sides and divide by the 1 plus x squared. So I'll get dy dx equals 2xy divided by 1 plus x squared. Now I'm going to multiply both sides by dx. So we'll have dy equals 2xy over 1 plus x squared dx. I'm not totally in separation of variables yet, but I'm really close. Because it's just a 2 times x times y up here, I'm going to multiply both sides by 1 over y, so I can get the y with the dy over here on the left. So I'll have 1 over y dy. This y times 1 over y will cancel, which is what I wanted. So we have 2x over 1 plus x squared dx. Now I can integrate both sides. So we should be pretty good at this by now. This is the natural log of the absolute value of y Over here, it looks like I can do a u substitution in my denominator. So I'm going to let u equal 1 plus x squared, therefore du will equal what I want it to be. So this is really the integral of 1 over u du. So this is the natural log of the absolute value of u plus c. U is 1 plus x squared, and there we go. Now from here, this is kind of a weird one. I'm going to subtract the natural log of 1 plus x squared from both sides. The reason I'm doing this is to use the quotient property of logarithms. And again, I'll call this c sub 1 because we'll have to change it. So again, when we have ln of a minus ln of b, we can write it as the natural log of a over b. So this is the natural log of y over 1 plus x squared equals c sub 1. I'm going to write this in exponential form. So going from log to exponential form, we would have our base of e to the c sub 1 equals y over 1 plus x squared. Again, my goal is to solve for y. This, again, is just a constant c. So this is really just c. Then I can multiply both sides by 1 plus x squared to solve for y. Hope you enjoyed this video. Thank you for dealing with my horrible voice right now, and good luck on your assignment.